Okay, so if you've observed one, as we just did in class, or any time, could be a kid on a swing, could be yourself on a swing, a pendulum is a pretty good oscillator. It repeats its motion over and over and over again. It doesn't lose energy unless something interferes with it, bumps it, etc. But in physics, bless you, we have to make an argument for why this thing should move the way it does, and then we'll test it by making predictions of how does it really produce the motion that our equations predict. So, this is a little bit sketchy at first, although if you look at my swinging bowling ball in class, the angle, that's actually pretty realistic. So we're going to assume that we have a small angle, less than 15 degrees. That's just to make the math easier. So in reality, of course, the distance, right, the displacement, let's write that like right here, that's good. The displacement of our pendulum is actually an arc along there, and so when the pendulum is located at this point, then we actually have an arc delta x equals theta in radians times L. That's the length of that swing out there, and maybe I shouldn't highlight this part. Okay, so from our 0 at the middle, we have a delta x like that. Well, if the angle is small enough, that's pretty close to an x-axis right here, where I would have like plus x like this, and minus x like that. So this, what's drawn in the picture, is a much bigger angle than 15 degrees, so you can see it. But if I had a really small angle, like, oh, look what the pendulum's doing back there. Okay, it's just budging back and forth. You can't really tell that it's lifting at all. Okay, so that seems pretty reasonable. Uh, but at the same time, we're going to do our old vector trick, just like we did with an inclined plane. Gravity, of course, points straight down, but if the pendulum swings even a little bit out to the side, we'll have a component of gravity that's trying to restore it to the center. And see how here's the angle of the pendulum up at the top, right there, and that's the opposite side. So this side in red would be mg sine theta. Okay, and we don't really need it, but just to be complete, this other side of the triangle would of course be mg cosine theta. But we're going to have a force of tension on the wire that's about equal to mg cosine theta. You could argue that it's exactly equal. We'll see. Okay? Any questions so far? Oh man, more friction on the bowling ball than I thought. It's barely going now. Maybe I wasn't taking such a risk. Okay. Aha. Well, I know I've made this argument before, I think. Yeah, I know I have. Let's see if you remember. If this arc length gets small enough, then I can treat it as straight. Okay? Like the sides of a triangle. So this angle here, really, the angle in radians, is the arc divided by the length, or the radius of the circle. So my angle is actually x over L. Okay? And if the angle is very small, then my sine of the angle, because look, that's also the opposite side here over the hypotenuse of the triangle, is also about equal to x over L. Okay? I'll scroll down for a bit. Anybody need, like, from that wide paragraph up? Drew the stuff. Great. Okay. Well, then from the picture, we have our net force equals mg sine theta. Okay, and that's equal to mg, because sine of theta is a pretty small angle, x over L. Okay, and then what we wrote down, well, the net force is the mass times acceleration. ma equals mg over L times x, and we can right away cancel those m's. That's a fun experiment, maybe for home, that we don't have time to do right now. Hang different mass objects from a string, the same length string, and watch them oscillate. Okay, give them a bump, time how long it takes to do one cycle or 10 cycles. And it will depend on the length of the string and not the thing, not the mass. But we just spent the whole time yesterday supposing and checking with an oscillator that if my force on the oscillator, my spring force, and there was no friction, mass times acceleration, was minus kx. Oh no, and there should be minus signs. It's in the text. Right, if x is displaced positive in the picture to the right, then the force is obviously to the left. Silly me. It's my first day back. I forgot. Okay. With a spring, we have net force, mass times acceleration, equals minus kx, the spring force, divide by the mass, and you have an acceleration that's equal to minus k over m, which is some physical constants. K is the spring constant too, remember, so remember k over m has units of 1 over second squared. And this is meters per second squared, so this is meters per second squared. And that gave a time, we demonstrated last time I was here, of 2 pi over, it has to be m over k, so that we get some seconds. Well, look at that. Here's a negative sign and some stuff in front of x. And acceleration has this relationship to position in a spring oscillator, like it did Monday. So we're just going to say for a pendulum, because acceleration and position have this relationship with a pendulum, we're going to say the time for the pendulum is 2 pi times the square root of the stuff. Only the stuff, look how I took k over m, had to flip it upside down to get seconds. We take L over G and flip it upside down and get seconds. Sure enough, meters in length divided by meters per second squared gives you G for the pendulum. So they're both oscillators. They have the same system. We do just like that. And sure enough, we find, like a kid on the swing, only the length of the swing, not the mass of the kid, makes a difference. And we instead of a spring, gravity's the driving force, causing it to swing down, keeping that thing going. So it does depend on gravity, just like it did the spring constant. We've tried this on the moon when people visited the moon to see that, yes, indeed, the same length pendulum slows down. So just for fun, on the homework problems, we ask about moon gravity or Mars gravity or something is less. You just plug in the different number for G. Or since you're honor students, we could give you what planet are we on, and I'm going to tell you the time and the length and everything. We'll figure out what G is. You could unwrap that equation. Okay. Any questions? We're that worn out. That's okay. I appreciate that. All your hard work and your determination. I still have not derived exactly why that comes out like that. On purpose. I'm saving it for tomorrow. What we're going to derive today, though, is something a little easier. Maybe you can work along. I think I can fit this on the same video. Yep. Okay. Just using conservation of energy. We'll go back to my spring oscillator, because it doesn't look as weird as the pendulum. If I have spring constant k, mass m, and amplitude, what was the amplitude of an oscillation? If you didn't write down what it was a couple days ago, you should make a note. This is like x max. This is the biggest displacement that this oscillator will reach, and unless it gets another push or something, then it can't exceed that limit of its displacement. Okay? So watching the pendulum or the spring, what's the velocity when you're at the amplitude? When you swung all the way out? This is actually the projectile problem. If I throw a ball straight up in the air at the top, its vertical velocity must be what, Calvin? Sure. Calvin's not made it. Aaron, go ahead. 1 over g. Well, that's how long it's going to take to get there. What's the velocity have to be at the very top? It has to be 0, because if it wasn't 0, it would either go up a little more or it would already be on the way down. Same with an oscillator. When it's reached the extreme, and that's the definition of amplitude, is the extreme displacement. When it's reached the extreme, it must be turning around to come back. Otherwise, that wouldn't be the extreme. So at that extreme, v equals 0. Okay, so at the displacement, to do this derivation, all you have to do, you might feel, well, you're so exhausted, so you won't. You'll feel good. If you still had another test, you'd feel bad that this is so much easier than rotation. In fact, sometimes I weight the oscillation test more just to give people a hand. But, okay. At the amplitude, your spring potential energy is maximum, and kinetic energy is 0. So if potential energy for a spring is 1/2 kx squared, then you have 1/2 k a squared. Okay? And that has to equal the total energy at any other time. So that has to equal 1/2 kx squared, whatever the displacement is, and plus whatever energy is still left in the spring. 1/2 mv squared. Sorry, there's kinetic energy and there's spring potential energy. Okay. Okay. At what x will the velocity be maximum? Even just from the algebra. Or even I swung the bowling ball, and I started right next to my face, and it sped up, sped through the middle, turned around and came back and stopped right at my face again. Because I know it's slowing down and losing its energy, converting back to potential energy, all the way until it touches my face, and then it just runs out. At x equals 0, v equals v max. So we can actually just drop that term. Okay, good. If I plug in 0, I should get v for x. V max is just, okay, all those 2's would cancel. I get k over m times a squared, and then I have to square root it all because I had v squared. So it's just the amplitude times, hey, wait a minute, square root of k over m. And I bet in a pendulum it's square root of g over l. There's that weird same two things in a fraction again. The plot thickens. Okay. Oh, I gotta stop. I'm gonna write this down and pause it. We could also even say, for any point, I could just take, let's see, if I just did a squared minus x squared, because all those halves cancel out, take the square root, and then what do I do with my m and my v? I had to divide by m, and they've got a k over m. Square root again. What does that mean? But I can actually plug in any x I want and find out what the speed is at that point.